Section 4.1 goes into more detail about how do you move data around from one place to another in the CPU. Let's take a look. The first thing we need to look at is the layout of a basic instruction. Now you've seen this before. The mnemonics and the operands, you've been using some. The label, we're going to worry about when we get to if statements and loops. That's coming up in Chapter 6. The comments you should be familiar with. Let's look at the different types of operands we can have. First, they can be immediate, like the 10 and the M. These are not variables. These are literal values that you're storing someplace. They can be registers, like the EAX and the AX, or any of the registers that you've studied so far. They can be memory locations, otherwise known as variables. num1 and ch1 here are locations in memory. Now we gave them names, and if you stop and think about it, that's exactly what you did in a high-level language. You gave memory locations names. Now you're going to be going through looking at different instructions more and more as we go along, and each one of these is going to have a code indicating what kind of operands that instruction can have. This table over here, table 4.1, shows you exactly what to look for. If you see something that look like this, either with a number after the word reg or without a number, you know that operand has to be a register. If you see something that look like this, you know that operand has to be an immediate literal value. Some of them say 8, 16, 32, or just in general immediate. Now then, this gives you the option. It could be a register or a memory operand. Again, 3 different sizes. And finally, if it just says MEM, you know that has to be a variable of some sort or some memory location. Over here on the right, we've got what's called a listing file from a little program I wrote. An upcoming video will show you how to get your own listing files from any programs that you write. The data segment starts at memory location 0. Now understand that's location 0 of the data segment. When you get down here to the code segment, it has its own address 0. So there are 2 different places in memory. num1 starts at location 0. It only takes up 1 byte, and you see that 2B is the hex value for the 43 that I stuck in there to start with. num2 starts at memory location 1, again in the data segment. It takes up 4 bytes. And the 15E is, again, the hex translation of 350. We come down to the code segment now, and the first instruction starts at address 0 of the code segment. The 8A and the A1, those are what are called opcodes. 8A stands for, hey, load something into BL, and A1 stands for move something into EAX. Every instruction for every different type of operand has its own opcode. And then we look at the memory addresses that are coded into the instruction itself. Notice this is the location of num1 and this is the location of num2. Now you might be wondering what the R means out here. When your program loads into memory, you don't know where the operating system is going to put it. So the R stands for these addresses are relocatable. And that'll happen every time your program runs. It's going to load someplace in RAM. You just don't know where. The move instruction. This is the one you're going to use more than anything else. There's some general rules that you have to follow. The first 2 are the most important. You really don't get into trouble much on the third one. First of all, both operands have to be the same size. If one of them is 16-bit, then the other has to be 16-bit. Doesn't matter whether it's memory or register. And the big rule that gets to be a real pain is you can't have 2 memory operands. That means you couldn't move data from one variable, if you will, to another variable. You've got to go through a register to do that. Okay, these are the operands that I can use for the move. Notice over here our destination operands can be either register or memory. Over here on this side we can have register, memory, or immediate. Now it makes sense I can't use immediate over here as the destination because you can't change an immediate value. It's hard-coded. You're always moving from the source to the destination. And keep that in mind on all these instructions. So let's put a little bit of code in here and kind of work our way through this. First of all, I'll load this big number into the EAX register. Now look what I'm going to try and do. I'm going to try and load into AX. Will that work? Yeah. And notice all it did was change the AX register. It didn't have any effect on these top bytes of the EAX register. That's important to get in your head. That EAX register can be treated as a 32-bit. The lower half of it, the AX, can be treated as a separate register. And then the AH and AL can be treated as separate registers, parts of the AX. That gives you a lot of options. So let's try and do this next thing. I want to move N1 into the AL register, and look what happens. It left this byte alone and just changed the AL register. Next thing, I'm going to load the hex value CC into the AH. Notice all it did was change the AH register. Didn't affect anything else. Now this movzx comes in really handy, and let me show you how. The Z stands for 0, and the X stands for extended. Let's take a look at this code. All right, the first thing I want to do is, like we did before, load up the EAX register with this big value. Now notice what I'm trying to do here. It won't let me do it. It being the assembler, why not? Well, because N2 is word size, EAX is double word size. Remember, the operands have to be the same size. I would just be prevented from moving the value in N2 into EAX if it weren't for this instruction we're looking at. Take a look at what I can do. I can change that instruction right there to this one. And watch what happens. It loaded the 9B37 into the lower part of EAX and just zeroed out the top part. Now this only works with unsigned data. If I go here, won't let me do it. Why not? N1's a byte and EAX is 4 bytes, being a double word. But I can do the same sort of thing and change it to movzx, and it's fine. Notice because this was 1 byte, it changed the 1 byte in AL and zeroed out everything else. Isn't that what 64 hex would look like if it were just in the EAX register? And the answer is yeah. We move down and we do this. We're just putting the original value back in. And now when I come down to the final instruction, N1 moving into the AX register, look what happened. It took the 64H and then it zeroed out the AH register. Just exactly what you'd want it to do. But this is a workaround around that first general rule. I can move a small value into a larger one if I use the ZX instruction. Here's something valuable to remember. The movzx only works when you're talking about unsigned data. This instruction is comparable to the one we just looked at. The difference is the S in this instruction stands for signed. Here's some code. Let's look at the data definitions first. Look at N1. The 6 out there on the left means that's a positive number. Again, we're talking about signed values. That's positive because that digit is less than 8 in hex. Notice over here what that really means. If you looked at it in binary, here's what you'd be seeing. That sign bit up here is a 0. That means it's positive. Look at this one. The top digit, the leftmost, is 9. That's greater than or equal to 8. That means that's a negative number in signed data because the top bit is 1. All right, keep that in mind. First thing I'm going to do is put a bunch of 2's into EAX. That's just to make it easy to see what's going on. The next instruction says move N1 into EAX. Well, now normally I couldn't do that because N1 is a word. But by using that sign extend thing, I can do this, and it moves it in there just fine. Just like we saw with the unsigned. This is the same kind of thing. It's taking whatever the top bit is here and just extending it through the EAX register, or whatever register you're talking about. Let's put our 2's back in. Now watch what this does. Now this time I'm moving a negative number into EAX. Since this top bit here is a 1, I want all of these to be 1s. Then I would have the right 2's complement value for that to be a negative value for me. And that's what that instruction does. Remember again, this one works when you're talking about signed data. This exchange instruction, notice I can only go from register to register or register to memory somehow. This lets you exchange those 2 values. Notice it takes 3 instructions to do that. Now you might be thinking, well, in high level, that's all it took. Well, it's what it looked like it took. It took more than that. The compiler was doing some stuff behind the scenes for you. In assembly, if we didn't have this exchange, it would take 4 separate instructions to swap values. Think about that. And you go, well, that's no big deal. Sooner or later, I'm going to ask you to write a bubble sort or selection sort on a bunch of values. You're going to be doing a lot of swapping values in either one of those sorting routines. This instruction right here is going to help you do that. For these direct offset operands, you're really going to have to get this down. Let's look at some definitions here. I've got 2 arrays. They're both byte arrays. And here's what all of this would look like in RAM. Now notice this array starts right after this one. So in RAM, it's all just laid out like this. And I do an instruction like this, which says what? Move the value stored at this location, array 1. Remember, array 1 is a location in memory. Without anything else, it means the first value in the array. So what's going to happen? What's going to be loaded into CL? Well, there's a 5H there, and that's what goes into CL. I do this instruction. It says move the value stored at array 1 plus 2. In other words, 2 bytes after the start of array 1. And this is how you notate it with the brackets. I know the book says you don't need them. Please put them. So what goes into CL? Well, there's an F stored there. That's what goes into CL. And then I do this. It points to the 8th byte after the start of the array, and it loads a 2DH into CL. No problem. That's working just like it should. And then I do this, and what happens? It's pointing here. But y'all, here's the end of array 1. What have I just done? I've gone into array 2. Well, why didn't the assembler tell me about that? It won't. So it loads that 46H into CL. That's probably not what you intended. It might be. There's some techniques that use that, but it might not be what you really intended. The assembler doesn't help you out at all. It doesn't check for array boundaries. Now, if you programmed in Java, you realize that if you exceed an array boundary, either on the bottom end or the top end, you get an exception thrown and your program stops, unless you're catching exceptions. Not here. Let's talk about this a little bit more. Okay, I'm declaring array 1, and here's what it looks like in RAM. Now, I'm writing these in hex this time because it'll help you see what's going on. And here's my warning out here on the right. Remember, we're dealing with little Indian storage. I'm blocking these off for you so you can see where the word boundaries are. So I do this. I want to move array 1 into AX. That's not the whole array. That says go to the location array 1 and move that value into AX. That works great. And I do this. here's what I want right here, right? That 37OD hex. And in high level, I'm thinking, okay, if I want the fourth thing in an array, I just put an index of 3 in the brackets. In assembly, here's what it gets you. Why? Because these offsets in brackets are measured in bytes. Now the compiler in high level was doing 2 bytes at a time for word size things, but not in assembly. You have to keep track of that. So that 3 says go here. Oh, it gets worse. And the thing surrounded in purple gets loaded into AX. Now remember, this is in little endian storage form. And so what does that do? That means when you pull it into AX, it reverses. Please look at this. When you're debugging a program, this is going to waste hours for you trying to figure out what went wrong. I promise, I've done it. Okay, here's what it's going to feel like every time it happens. Now, if you wanted to do it right, you'd say, well, okay, every one of those words is 2 bytes. So to get to that fourth one out there, if my high-level index was 3, I multiply that by 2. And it gets me what I wanted there. Now, I certainly want you to read the assignment in the book. What I tried to do here was just hit on the spots that I think would give you the most trouble. That said, if you've got trouble with anything, please get in touch with me, because this just compounds if you don't understand it now. Thanks for watching.